Tap. Hey, it works. get better reliability with SLOs. This is heavily adapted from Datadog's SLO workshop that we're performing at Dash, assumedly, and our upcoming summits. Now, the subtitle for this, because it doesn't make any sense until you hear it, is SLAEIOU and definitely why. But no matter how I tried to write it, it just doesn't make sense until you hear it. So what we're going to cover today are specifically the SLIs, SLOs, and SLAs and what those mean, defining quality targets, error budgets, and some practical examples. But you may be wondering who that bearded beauty is and why is he talking to me? Well, I'm Waldo. I used to be a productive member of society before I took this job, but I come from a systems and ops engineering background, spent a lot of time in the DevOps community doing SRE type stuff. But before I accidentally went to the right conference, I used to be a fairly typical bitter, angry sysadmin type. The DevOps community was still pretty new in 2011 when I first went to Velocity, but it was revelatory for me and really changed my life. It literally changed my career in so many ways, because at that point I'd simply never been in an organization that didn't have a contentious and sometimes even antagonistic relationship between the people who made things and the people who made them available. Now, because of this and the relationships between DevOps and SRE, I'm here to talk about one of the steps that enables a healthy transition to incorporating DevOps and SRE practices into your organizations. So technical people love acronyms, and in this case, we've got at least 3 TLAs that are very similar, so it's easy to get them mixed up. So we'll start with some nice, tidy definitions. SLAs. These are, as you can see, a quantitative measurement that expresses a particular aspect of a service. It's often a metric, but it doesn't have to be. The other key word here is quantitative. You have to be able to measure it with a reasonable degree of accuracy. It can't just be a gut feeling. SLIs are part of the basis of SLOs, so we'll look at that next. These are a target value for a service as measured by an SLI. Wow. The idea here is to pick a reasonable value that should be maintained or strive for in a given SLI. And we'll get into examples later, but the core here is that it's a target, it's a goal. And you don't necessarily want to exceed that, which we'll come to later. This is ultimately a way of measuring the success or failure of a service over time. Now, SLOs build on SLAs, which if you've worked in tech for any amount of time, you're probably much more familiar with. Now, this is a contract that defines the results and consequences of meeting or not meeting your agreements with your customers, whether they be internal or external. Like agreement, promise, and contract are all words that are often going to be associated with SLAs. And they can have, for instance, financial penalties. The important here is that it's a statement that codifies what happens when an SLO target is missed. In principle, the result can be anything, but it's commonly a business decision or has a financial repercussion. Now, as you may be able to guess, there's more than just monitoring tools at play. It's really a team effort that comes to identifying, scoping, and defining, and ultimately implementing your SLIs, SLOs, and SLAs. So you want to focus on the user experience, and your users are anybody who consumes your service, whether they're internal or external to the company, other services that build upon your product. It doesn't matter. Anything who consumes what you produce. So let's talk about what quality targets look like. The user experience is first. in the end, everything should come back to thinking about the user's experience. So how do they interact with your product? How do they use their product? What's their workflow and where do you fit in? What services do they interact with? And what do they want? What do they expect? We'll come back to these. So not everything makes a good SLI. Like, nobody cares about your CPU utilization. They probably don't care about your memory. And as long as things are working, they don't care about any of the system stats for the most part. Values are metrics or events, typically. Now, there are a lot of metrics and rubrics that you can use to find a good SLI, but using things that make sense for the type of service that you're providing, using may not apply to the type of service that you're running. Reliable failure conditions are also indicators too, and you should be able to answer why. Apologies, I live in Florida, so everywhere I go is dry in comparison. So SLOs will have both a target and a time window. And it's not uncommon for them to also be like a complex statement, including percentiles of a metric over a given period of time. As I said, indicated before, there's usually a penalty associated with SLAs. They're often financial. This is much more common when money is changing hands between individuals or corporations. If you're doing this between teams and orgs within the same company, it's, well, indicative of several things usually. Now let's talk about error budgets. It's fun to think about moving fast and breaking things, but let's move fast and fix things. Failure is going to happen whether you do anything or not. So how you respond is important. The idea behind the entire SLO concept is that you can balance innovation and novelty with reliability and stability. So your error budget comes from your product team and product owners. The actual objective should be measured by, like the SLI, the indicator, should come from a neutral party like your monitoring services. Now, the difference between the measurement and the objective is your error budget. Now, just like budgets in most large organizations and government, if you don't use it, it goes away, and you want to spend as much of it as you can without going over. If your SLO is being met, and say you have an outage, unless it's very critical, you don't necessarily need to jump on it. You don't need to treat it as an alarm. You can come back to it when you have a few minutes. You can treat this as downtime. You can treat this as an opportunity to test out a new version when you might have otherwise had to plan something. Now, if the budget is 0 or negative, you should be concentrating on reliability. It's at this point that new feature development stops and you start going on bug hunts. Now, how many of you do like bug squashing sprints or projects where you go through your backlog or your previous incidents and try to squash bugs? Show of hands. about half of you. That's actually impressive. This is a way to make this a more common part of the cadence, and it also encourages you to do this just as a regular part of your sprint planning, or maybe as the bonus. What do you call it? Your stretch goals for the sprint. Like if you get your new features done, you can also already plan to squash certain bugs ahead of time. So, practical examples. What does this look like? I co-wrote this with a friend of mine, Daniel Marr, who you may know as Frosty on Twitter, and he likes to subtly screw with me in a lot of ways, and I mean, it goes both ways. But the character at the end is pronounced F, so this is photosite.nef, which is fun to say, but also critically not real. But we have to consider, for our hypothetical service, we have to consider how the users are interacting with our service. They're clicking around, they're viewing photos, they do searches. Their workflow, they log in, they upload and search for photos, they view, pull things down. And the services that comprise what they think of as our site have account backend, upload services, storage features, and so on. And what do they want? They want it to be there, and they want it to be fast. So, our indicators. For the responsive request, could the server respond to it? How long did it take? And how many requests can we handle? Are we scaled appropriately? As far as storage goes, can they get what they want when they want it? How long does it take? And is the data there when it's needed? And as far as pipeline goes, did they get the right thing? Are they a cat person and accidentally got a dog picture? Is our index completely messed up? And how long does it take for a new photo to be available for their view or for others to search for it? So, some more tips. I work for Datadog. We have an SLA product. And this is a way to make it easy for you, because a lot of other things don't have this built in. We make it easy for you to figure out what SLOs work for you, but also make them transparent to the teams that you're working with, so you can show across the org how you're working right now and if you're meeting your agreements. But these are typically based on monitors, and these are often tied to metrics, but they don't have to be. This is typically, like I said earlier, a value per period of time, and can often be a percentile if you prefer. Now, we can also do event-based, which are typically thought of as logs, and this is essentially a success ratio. Now, is anybody not familiar with the four golden signals or red? Okay, that's fine. So the four golden signals, I believe this came out of a Google paper, but I mean, it was formalized in a Google paper, if I remember right. These are four things that you can with a strong degree of confidence, apply to most any type of metric or service. How long does it take for a request to a response to happen? How much traffic is incoming to your service, and are you scaled appropriately? What is your percentage of errors, and are they coming from your user or from your service or services you depend on? And how can you mitigate those? It allows you to start thinking about how you can mitigate different areas of that. And the saturation. How much of the capacity do you have are you using? Now, no matter what you do, again, focus on your users. It's very easy to get caught up in the weeds and forget, but the users are the reason that you're here and that you do the work that you do. So define your user stories and your journeys first. Figuring out your SLIs and your SLOs comes later. Involve all your stakeholders as well. especially product. I know, so part of, it's not DevOps days anymore, but I consider DevOps to be about the business, and that includes everybody in the business. That includes like straight up product people or accounts receivable and your legal team. Anybody who has a stake, which is really anybody in the company who can provide value, should be included. This is one of those things that you can and should start small and iterate with. It's kind of, most of the organizations I've been in demanded 100% uptime, and it's not healthy. So it can be uncomfortable knowing that something is broken, knowing that something that user-facing is broken, and not stopping what you're doing to go fix it. But you have to let that go. And no, I'm not singing. But realize that the error budgets are there to make your life better and ultimately to make your customer service better. It's okay. Like, not everybody needs everything to be available all the time. So building out, it can take time to figure this out. So starting off with SLOs, a good way is to not make them strict. Start establishing a baseline of, like, do people actually start complaining if I only have 2 nines of availability? Because there's usually a significant cost difference between every 9 or 5 of availability that you add. So find out if that's even, like, is 4 nines even necessary or reasonable? It's probably not for a lot of things. So in the beginning, err on the side of naivety. And these are some hard-won lessons from Datadog's own SRE team. Should keep in mind that these are not written in stone. Your SLOs can and should change. You should reevaluate these, especially as not just your environment, but within your company and your entire ecosystem changes. SLEs have to have the capability to evolve as well. And if you don't have a way to do this, to make it very apparent, at least to the people within your team, grab something. I don't care what tool you use. Like, I'm an evangelist for Datadog. I would love for you to use Datadog, but I still want you to have the insight tooling that you want and deserve, something that makes your life better. Now, as a bonus, we have some more letters for you. So like I said, SL, AE, IOU, and definitely Y. I've worked in places that didn't have one production environment, but they had like 30. Everything, any fault, any flaw was considered pager worthy, even though only one environment was user-facing at a given time. Now, these were things that were called staging or integration or load test, but their corporate culture was such that if anything was broken, if anybody could consider it a blocker to what they were trying to do at the moment, it was a pager-worthy event. This is not healthy. If you have multiple environments as part of your SLOs and your API documentation, you should be clear about what things like your staging environment is for and needs. Is it for your team to test things, whether a new feature or test your deployment mechanisms, or is this for other teams to test their integrations with? Now, once you've defined what that is, what your, say, staging environment's for, then describe what your SLO is for that environment. It should be nowhere near what your SLO is for your production environment. Let's see, we've done SL A, E, I, O, and that's it. So SLU is for updates. Again, they're not written in stone. You should periodically review them. Ask yourself if they make sense. And then, you know, are you targeting the right uptime? Does it make sense? Now, something that's happened to me plenty of times is I'll throw out a proof of concept and find, a month later, unbeknownst to me, it's become mission critical to the company. Everybody uses it, loves it, depends on it, but I built it on a single VM with no load balancing and no backups, so on and so forth. It's something I hacked together for a few minutes, and it happened to be useful. Well, did something become more important than you realized? So this is something you need to coordinate with your other teams. Likewise, if you're a 3.9 service and there's a 4.9 service that has hard dependency on you, well, that doesn't work. You cannot be dependent on something less reliable than you unless you take significant actions to mitigate that. So you need to identify the hard requirements, and if you can't engineer around them, you need to spend effort in improving your own resiliency. I mean, it's just surprising how common it is that like a proof of concept just kind of slides into production and just absolutely mandatory, mission critical. So when it comes time to pull the trigger on making a service level update, put out a quick survey to your peers, to your fellow product teams, or RFC it to your customers, again, internal or X. And when a decision is made, broadcast that information. Update your docs, update your SLO widgets, and communicate it. Let fly that email blast in all its glory that nobody's going to read, but at least you have sent it to your internal customers. And finally, we're going to do SLY, more properly spelled SLWHY. This is really the first step towards bringing sanity to the operations of your products. In too many places, like I mentioned before, any outage, any disturbance in service is considered an emergency, and it's just not healthy. If our businesses demand 100% uptime, we don't have time to experiment or innovate or even make healthy mistakes. Here's the thing. The truth behind building individual crickets. All right, fine. The truth behind building individual services so that they're better resilient to faults in their dependencies makes for a better user experience. Additionally, having a healthier relationship with faults by preventing every single one to be a 3-alarm fire allows teams to more comfort and flexibility when those faults do and will appear. Now, this also allows, because they're not such a stressful thing, individual product teams, especially engineers who have not spent a lot of time doing operations, if there's less of an emergency and fire drill attitude behind it, they're going to be much more willing to take on their own resiliency by owning their own uptime and availability of the services that they create. So what we've covered today is SLIs, SLOs, and SLAs, as well as the other vowels. We've talked about defining what quality targets look like, error budgets, and shown you some practical examples. I am with Datadog, so of course I have to plug my dear beloved employer. If you're not familiar with us, we're a premier insight tooling and observability platform. We have a booth out there. We are a fine purveyor of excellent conference t-shirts. I don't have any with me. I mean, this one's slightly used, but I'm pretty sure we have more at the booth. And we have a free trial that's very low impact and gives you access to everything, including our fantastic support. So with that, I want to thank you very much. I love you all. Thank you. And if you'd like, I have some stickers up front. Have a wonderful day. Thank you, SCaLE. This has been my first SCaLE, and I forgot to say, be gentle. You've been gentle. Does anybody have questions?
Can you talk about the different S's in relation to like downstream dependencies? You started touching on it, but I want to understand how more, even if they have the same number of nines, how do you do the first one, like the second one goes down? Like how do you like what happens? You know what do you kind of see what I'm saying? Like,
how do you deal with your dependencies when run as a...
Within the org, you have the front end and the back end.
Yep.
And there's obviously joint SLAs between each one, but for different groups and stuff like that. How do you write those into the SLA? The different SLAs.
Okay. The question is, how do you, say, document and identify and deal with the SLOs when you yourself have dependencies? Okay. So this is an exercise that should start perhaps low in the ecosystem, low stack-wise. So you can start with like your storage and your load balancer availability and things like that. A healthy step in, I talk about this in other things, I left it out here. A healthy thing to do is identify all your requirements and not just, hey, I call to our authentication service or our inventory service, but like, I need LDAP to work, load balancer access, be as silly as you want, but identifying requirements that you have, things you need to work in order for your service to function. And if possible, especially if those are internal services, ask them to start thinking about this. It doesn't have to be an initial SLO, or it can be an initial, it doesn't have to be as formalized yet, but start getting them to think about it and publish yours as a draft SLO, or like as of this date stamp, we are targeting this, but you could list risks and dependencies. These do not have defined SLO targets. And just be prepared to, especially in the beginning, iterate more often on how often or what kind of SLO you're actually targeting and what's reasonable for you to expect given the availability of your dependent services.
Okay.
Does that make sense?
Yeah.
Oh, good. I was afraid I was word salading there.
Good question. So I'm familiar with SLIs, SLOs, SLAs, and the question is, what pain points do you see trying to migrate to a system, getting a team to work together to identify and collect those SLOs in a useful way so that you get your action on?
Is the question, how do I get teams to like participate in this exercise at all and start thinking about SLOs so that you can do it more broadly?
Yeah, that's a multi-part question. Team was part of it, but also like, you touched on identifying like portal vendors, you touched on identifying those, but putting that into practice, I guess, is really the whole entire question. What pain points do you see there?
So a pain point that I see in getting teams and individuals to participate in like identifying what their SLIs are, what a reasonable SLO is a lot of people might not think it's important. Why does availability matter to me? Well, if you're a software engineer who's not responsible for your product, I'm not going to give my rant now, but you should care because resiliency is the one feature, or I'm sorry, availability is the one feature that any product needs. And without availability, it doesn't mean anything. Availability is a result of resiliency, and you have to be able to know what you're measuring that by. Whether it's the response, a response time, whether it's successful or not, or a percentile of successes, or whatever. So this kind of goes to the software testing versus monitoring. You want to they don't have to have a one-to-one relationship, but they should be measuring the same level of success. So your software engineers and whoever is running them, or hopefully them, know what, this kind of goes into KPIs, like what is the one thing my team is measured on? Or that's a way to look at this, is your SLI is the one thing that you're using to measure your service, having acceptable availability. So driving that point home, that that availability is a key is the primary feature, followed only then by its like core functionality. Because without the availability, their feature is meaningless. Does that make sense? Does that answer your question?
Yeah.
Okay. So explaining the why, like we want to be able to, we want to measure, we want to do. You can go into, there is a whole dark world of value stream mapping that's only kind of touches on, but identifying what your dependencies are and how available they are, how resilient they are, is a big step in being able, and don't get me wrong, this will have some unhappy conversations. It's entirely possible that there are some teams that are much more that are very dependent upon by a lot of teams that are not as available as they really should be, as they need to be. So roadmaps are going to have to change. And I didn't get into this in here. I forgot to. I left it out, unfortunately. When you are in excess of your error budget, there's a consequence. Now, nobody should be getting fired. Nobody should be like a performance review or PIP or whatever. It should mean new feature development stops, and you fix the problem, and then you fix like some of the contributing factors for it. Build up the resiliency with that remaining time. Now, your product manager, owner, or scrum master might be upset because your burn down chart's going to change. Tough. The availability of your feature is more important than the new features coming out. So that is another conversation that needs to happen, and your management needs to be okay with that. Otherwise, none of this works. Yes, sir.
So as you touched on in the answer to the past question, like
Yes.
SLOs need teeth or consequences if they are the customers are internal or the agreement is internal. Can you speak a little bit more about, or maybe examples you've seen of successful consequences or successful processes for these consequences to ensure that SLOs will be met in the future?
The question is, what are some examples of consequences when an when an error budget is exceeded? And it's really just sticking to that budget. If you are under budget, if you use up 99% of your budget, you're fine. No consequence at all. You just keep doing development as your ticket tracking system allows for. But once you exceed that threshold, you stop doing new feature development, and you work on resiliency. That really is the main thing. There is a talk by Jennifer Petoff. She is, I think, Senior Program Manager at Google for SRE education. And she gave a fantastic talk at All Day DevOps this past year that she goes a little bit more into the why and how this builds into SRE, and she talks a little bit more about penalties, but it's really just not that complicated. Like the penalty is you stop doing feature development and you instantly prioritize the resiliency and availability. Does that answer?
Yep.
Okay. Yes.
So I first see this as like a evolution of metric collection thing. So I'm wondering, are you still tracking things like CPU and RAM, and maybe just keeping that as your little ops area? Look at it for debugging, or is it even not worth the overhead if you're looking at these higher level things that are somehow connected to those possibly?
So the question is, do you still do metrics collection for system level metrics when you're doing SLO? Yes, and not just because I work for a monitoring task. Like, those metrics are still useful, you just probably don't need a dashboard for them right away. And you certainly don't need to alert on them. This is a more higher level thing, one for transparency and communication between teams that, hey, if your team, let's say I'm a shopping cart team and I depend on an inventory team, they only have 3 nines, and maybe I have the same, the same SLO. It doesn't matter what my SLO is really, but if they're broken, and I go, hey, my people can't, the customer cannot look at the inventory. We are unable to add something to their cart from the inventory because your service is unavailable. Can you please go fix your thing? Well, the first step in a healthy SLO environment is you look at their exposed dashboard of SLO and say, well, we're within our error budget. So you have to sit down and chill for a few minutes. But this is also where the SL updates come from, is, look, this happens too much. We get a bunch of calls from them. We really need the inventory service to be more available than it is now. How can we prioritize that? Or are there other ways of making changes to things so that they're less user impacting, but maybe still allow you to have some downtime and innovate that stuff is still available in another mechanism, whether it's caching or blah, 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 whatever. Does that answer? Okay, thank you. Yes, sir.
When I start thinking about SLOs, it's usually the aggregate. Here's my site and this is available, and that's the one that usually gets from the customer. But we know that underneath that there's a ton of services that make that up. What's the best practice in saying, well, yes, the site's up, but these features or these services may not be. When it goes to reporting accurately that high level, do you dismiss the lower level, or how do you correctly, is there an industry standard on rolling, well, any given services offline that is the higher level service?
That's what I was trying to ask too.
Okay, so the question is, if my service works, but not all the pieces work, how do I report my service's availability when not all the features are available? Okay, so that is a great question, and this kind of goes back to like the velocity community, the web ops stuff of a couple of years ago. Is there was a lot of focus on, or especially a lot of talks on graceful degradation, where if a feature is not strictly if you depend on, say, like a sidebar that's being displayed. If it's not displayed, but it's also not a core feature of what your product does, it's probably okay, and you're not going to be dinged for that. They're certainly not going to show the availability for that period, but hopefully your customer doesn't miss it. But Google and Etsy and Netflix and like all of our favorite products and sites, you'll notice that things either load lazily or sometimes a feature just isn't available at the moment. It seems like the My List in Netflix has been taking a hit lately, just from my experience. But like I can still use Netflix and do other core things, even if it's slightly less convenient for me. But my SLO, like the front page SLO and being able to click a video or search for items, that's still available even if not everything has loaded or is available at that moment. So if you run the front page and there's a widget that's not available at the moment and it doesn't load, that doesn't affect you. Does that make sense?
So it sounds like you said if it's considered a core feature, it would affect the top bottom line.
Yes.
Feature, maybe that's
Yes. If a core feature is unavailable and you're dependent on that, this goes back to you have to be, if it's core feature, they have to be at least as available as you are. Does that answer the question? Okay. Any other questions? Yes, sir.
Does Data.gov give training on exactly this to like people that aren't here to a wider team, and mostly like management executives, directors, things like that? I believe we are road mapping a course in our training center. We have workshops at Dash and our community summits later this year. We have a lot of documentation on our site. We may have videos, but don't quote me on that. An earlier question, like, do we still care about like system CPU metrics when we're doing this? I believe that was from Liz.
yes, you still care about those metrics, you still want them available when you're looking into a problem, but they should be less front and center. And again, SLO is more a tool for you to be able to like determine, to prioritize, do I have room to continue doing feature development, and advertise that you are upholding your promises to the other teams in your company. So yes, all those other metrics that you're already using, they don't become worthless. You still need them to diagnose and fix things. Any other? Yes, sir.
The SLO, which is the piece you were showing,
Yes.
is that part of the core offering of Datadog, or is that an add-on?
I believe it's core. Jeremy? SLO, that's not a separate feature right now, right? Yeah, so you can just start playing with it. And you can also, I think you can, this is my work for like the next week, is working on the workshop, but I believe you can work with it in monitors as well to like actually alert you when you exceed your error budget. It's in beta. Thank you. Anything else? All right, you've been wonderful and have made my SCaLE experience wonderful and lovely. Thank you.
Sound check. Okay. We'll start in about 7 minutes. Okay, looks like it's time to get started, and today we'll talk about eBPFTrace. Now, first let me ask, anybody here familiar with Dtrace? Wow, lots of hands, looks like I'm in trouble. And what is about familiarity with eBPF? Okay. Fair amount as well. So, what we're going to talk about here is I'll do a quick refresher on Dtrace and eBPF, right? For those who are not familiar with those technologies, we'll look more particular about eBPF tools landscape and specifically about eBPFTrace and how it compares to Dtrace. So let me start with instrumentation basics. Now, maybe on the entrance you've seen we are in the observability track, right? What is observability? It's really ability for us to see inside the running system, so we can observe it, right? Fix it when it breaks, right? Or to make it better, even if it doesn't break, right? And that is understood, I think, pretty well those days as something is very essential, especially as we are dealing with increasingly more complicated systems, right, with microservices, you know, multi-layer architectures, and so on and so forth, right? And if you look at the approach to that observability is done through various instrumentation, right? Which you can see those like little holes and windows in the system, right, where you can see what is going on inside, right? Now, if you think about the instrumentation, right, they are you can slice and dice it, right, from different ways, but one of the approach would be to look in the static and the dynamic instrumentation, right? So what is a static instrumentation? Well, that means there are some sort of very specific, you know, counters which, right, or other ways which exist in the system. For example, we are all here familiar with Linux, right? It has and for years had a wonderful thing called procfs, which expose all kind of wonderful counters and so on and so forth, right? Which are essentially the part of static instrumentation, right? Dynamic instrumentation is when you, as a user, can choose what exactly you want to instrument right now, right here. Right. Now, another difference, I think, in instrumentation approach, which you also notice, is tracing versus sampling. If you think about the tracing, what that means is you have some instrumentation points in the code which emit some sort of event when that point is triggered, and then something happens from this event. Right? When I speak about, mention about static instrumentation in procfs, right, you can think about what in many places in code we have some very simple program, right, something as simple as implementing the counter, right, being called, right, and that you can think about event being generated, right, and processed all in one place. It's just a very simple code point, right. The sampling is another approach when you can say, well, instead of looking at that in the code, we can sample and observe a state of the system, right? For example, many times a second, right? And through the state of a system, for example, program stack, kernel stack, right? All kind of, you know, CPU diagnostic registers, we can also understand what is going on, right? That is pretty much another approach in this, to the instrumentation, right, especially in terms of performance analysis, which we can see pretty well, right? So this is a quick comparison between our static and dynamic instrumentation, right? Now, if you look at the static instrumentation, it is, of course, very helpful because it provides us a lot of data which is in standard format, which is ready to use, which is always available. But obviously, it goes in the only so far, right? Because if you will try to add too much of those kind of static instrumentation, right, then we will create a huge overhead, right, by doing so. In dynamic instrumentation, though, you can choose what to instrument based on certain conditions, right? So, for example, if you need to debug the system or something is going to run, you can enable that, right? Or you may, if you have multiple systems, you can have one of them like a canary, right, or whatever you want to call the system, and you can route smaller portion of traffic to that system while have more diagnostics enabled through dynamic instrumentation, right? So you can understand what is going on, right? And for dynamic instrumentation, you can go very, very deep, right? Okay. Now, Dtrace. What is Dtrace, right? And why is it cool? The Dtrace, right, as the name implies, that is a dynamic tracing framework. And it has been around for, well, look at that, almost 20 years now, right? So it started developed in Sun Microsystems in 2001, right, was released in Solaris 10 in 2005, for us, 15 years ago now, right? And the approach to that is what there have been specific trace points defined in user land and kernel, right, which can simplify the tracing, as well as you can also, through dynamic tracing, simplify or trace any function calls, right, and some other events. What is very cool and important about the Dtrace, right, which is marked in red here, is what the design goal was. What if a trace point, right, is not enabled, there is no overhead, right? So it actually does something, pretty smart. When if you enable a trace point, it essentially rewrites some of the code, right, to enable that tracing, right? But if the event is not enabled, then a program just, proceeds with no overhead, no specific, if trace enabled, then call that function, right, or some other overhead like that. And for Dtrace, for defining the program, right, for the instrumentation point, there was a special language defined called D language, right, which is something like C married oak, right, and they had a beautiful baby, right? Maybe not so beautiful, depends on what your point of view, but yeah, there it is. Now, Dtrace has gained some popularity for years, well beyond Solaris, right? It was integrated in macOS, in FreeBSD, in NetBSD, the Oracle Linux, forever supported Dtrace, right? And the code was even relicensed relatively recently as GPL v2, right? So Oracle would say, hey guys, we want now everybody to include that. And last I heard, there was also work to include Dtrace in Windows. Now, if you look at the Linux, Dtrace is kind of has an interesting story here, right? Dtrace is not available in a stock Linux kernel, right? Oracle has provided patches. Hey guys, you can include them, but perhaps that is too little, too late, right? If that would be done, decade ago, right, or 5 years ago, perhaps it would matter. Now the Linux community has pretty much standardized on using BPF, right, and related technology for that, right? So Dtrace in Linux, while you can get it in Oracle Linux, you can perhaps apply Oracle patches, right, where it is not really readily available in any major Linux distributions, like last time I've seen. Okay. Let's take a look at the tracing in Linux specifically now. Now, I think what is interesting is what Linux, through years, has gotten large number of those kind of competing tracing frameworks, right? I mean, if you look in this case, landscape, it has been getting you know, pretty complicated. Now, I'm not going to go and review all of that. I'll just send you to this wonderful blog post about the Linux tracing in pictures by Julie Evans. I think that's a very fantastic representation to see what is out there exists, right? But if you think about that, about the tracing, there are several kind of components which are important, right? You can break it down in the type of kernel interface, right? Essentially, what you can kind of connect to, right, as a probe. The type of program, right, which you can connect to that program, which can range from, let's say, built-in kernel buffer, right? So, for example, some of the tracing framework would support the native support in kernel, where you can say, hey, you know what, we'll have some buffer in kernel where all events would be logged, and then you can consume and process that from user space as you like, right? Another approach which existed in a while, like through System Tab, for example, sysdig, right, and some others use that approach in the past, is having a kernel model, right? Hey, you have a kernel model. That's how you connect that program which does the processing. Well, that is good, right? You can really do anything you want with that kernel model, right? And it's you know, very powerful, no restriction. But that also comes with the same problem, where you can do anything you want, right? That means potentially by inserting that kind of instrumentation model, right, into your kernel to debug something, right? If there is some bug in that model, you can pretty much screw up all the kernel and crash, right? And then you also have that kind of interesting challenge potentially as kernel version changes. Do you recompile? What if you forgot, right? And all the kind of risks, right, which come with that. So that wasn't very much allowed, right? And the last piece is the front-end tools, right? So even if you look at the very basic static tracing, right, which I mentioned in Linux, like a procfs, we have a whole bunch of tools like SAR, TOP, vmstat, which essentially consume that information and present that in convenient point of view for user view, right? The same applies to the dynamic tracing, right? And there have been a whole bunch of front ends developed through years, right? Some which I list here. Okay. Now let's take a look at eBPF. Right? As I mentioned, there has been a lot of different approach tried in Linux, but for the last few years there is a lot of standardization being done specifically at the eBPF framework. What is eBPF and where it comes from? It's interesting what the name BPF really starts from a Berkeley packet filter, right? Have nothing to do with observability, monitoring, right, instrumentation, or what's not, right? And indeed, that is where it came from. It was really developed in 1992 as efficient virtual machine for packet filtering, right? Pretty much for firewalls and stuff like that, right? And then extended Berkeley packet filter, that is new and improved version, right, which is exists in Linux. Now, what is interesting is when it comes to Linux, eBPF is what exists in Linux, right? So you often hear people just drop an E and talking about simply BPF in Linux, we are referring to exactly the same thing, right? I mean, I haven't seen particular original BPF being used in Linux context. It developed in a general event processing framework, right? So it is used by for observability, but it has other uses, right? Even in the network space, for example, people are using BPF for routing, for DDoS protection, right, and some other stuff. But we are focusing on, in particular, on observability. Also, through the years, the JIT compiler was developed for eBPF, and that means what even if BPF uses its own kind of bytecode, right? It doesn't use the native instructions. It can achieve very high efficiency. So, how does eBPF vs BPF compare, right? This has probably only like historical interest, right, for people, but that is how. In BPF, we only had, 32-bit registers in very limited number of them, and we had a scratch pad. In eBPF, we have 64-bit registers. There is many of them. We have a concept of a stack, and what is the most important, I think, here is those kind of maps, right? What is the maps is different data structures which can be used by eBPF program to store information. Like hash map, right? If I want to, I don't know, say, compute, some sort of distribution, right, or whatever, like histograms, all this kind of stuff, right, which is really allows us to do some very powerful data processing. eBPF was in Linux kernel since 2014, right, and which is great. That means is what you can by now find eBPF in pretty much all the modern Linux distributions, right? Because typically it takes time for them to embrace the kernel, right? And then often for companies it takes time to migrate to some particular version, right? So for example, 5 years ago, while it was in Linux kernel, it was not really readily available for most of us in production, right? You could install some, latest Fedora, right, and play with it, but in majority kernels which we are running in production did not include BPF. Now it changed. It's still being actively developed and improved, and what is also very cool is now it's a integrated Linux perf system, right? So some of the basic dynamic tracing can be achieved using that tool chain. So here is some example what have been done in latest Linux kernels, right? And you can see there is whole bunch of improvements continues going on. Okay. Now, I have mentioned what eBPF is actually like specific bytecode, and when we refer to eBPF program, that is a program which was compiled to that particular custom bytecode, right, which is where to be loaded in the kernel. As I mentioned, that is something which is safer than getting your random C code from the kernel loadable module. But it actually gets better. The programs, eBPF programs, they are verified before the load, right, with some sort of code analysis, so it prevents misuse, right? So, for example, you cannot really have the never-ending loop, right, in the eBPF code, right, and stuff like that. So it doesn't mean you cannot screw up your kernel, right? People are ingenious pieces when it comes to screwing up, right? But there is the significantly lower likelihood of you doing that, right? And if you don't, at least by the accident, it's much less likely to screw up, right? Now, while you can, probably check out some BPF code, right? You're probably not going to write in that kind of BPF assembly in your life, right? Why? Well, because actually LLVM CLang can now compile to BPF as a target. So you can actually write limited, of course, write about some C programs which compile to eBPF. Now, what is also important to note in this case is what that compilation is a kernel dependent, right? So when you are using BPF programs, then often you would want to have a kernel headers, right? Because then you compile some probes, right? It needs to know the types of data, offsets in the kernel structure, and so on and so forth, which can change in different kernel versions, right? That's why headers are needed. Okay. So if you look at the kernel space versus user space, how do those all play together, right? So if you use, if you look at that, right, from the user space, you would use a program, right, like eBPFTrace, for example, to generate that byte code. Then it will cause a load call, which will trigger to kernel, which will verify the program. If a program is valid, if you have all the permissions, like that will be loaded. That program can connect with all the different data points, kprobe, viewprobes, trace points, perf events, right? And as it runs, it would store the data in the map and still user space, right? And then this data can be read asynchronously to their various statistics gained by the front end, right? And that can also be output, right, through perf output directly from BPF is needed, right? That's kind of how it all works in a nutshell. Another fancy graph which highlights what different versions of Linux has gotten different instrumentation points. This is maintained by Brandon Gregg, right? Anybody heard about Brandon Gregg? Okay, yeah. So he has a fantastic blog, right, which writes a lot about BPF. It has those fantastic illustrations. I would suggest you to check it out if you want to learn more. And he has also released the book about eBPF recently, right? So if you really are interested about this topic, that is something great, great to read. Now, another project which you want to know is IOVisor. So IOVisor is where a lot of tools like BCC or eBPFTrace, even in part of that project. And while a lot of those tools would have versions which may exist in the latest Linux distributions, they are kind of relatively outdated, right? Because it takes time, and because that is such actively developing ecosystem and framework. If you want to use like the best feature, it's often best to grab those tools from IOVisor rather than to use what comes with operating system. Okay. Now, another thing to mention about eBPF is the overhead. This is something, the data from Cloudflare, right, in terms of they are using eBPF extensively, and they wanted to monitor, to look at the overhead. So what they have done in this case is looking at no probe, right, to see how much certain, let's say, operation takes, some simple probe, right, and more complicated probe, right? Some updating some stuff in maps, right, and so on and so forth. I think this is very interesting to see is what you should expect the single eBPF program call to take somewhere in the order of hundreds of nanoseconds, right? And of course, those can be executed concurrently, right, in multiple CPU threads, right? That can give you an idea how frequent events can you really potentially trace with eBPFTrace, right? You can see in this case you can, probably trace something which, up to a few millions a second, right? Especially if you have multiple CPU cores, right, with tolerable overhead, which is a pretty high number, right? So if something just happens, I don't know, let's say 10,000, 50,000 a second, right, that can be usually profiled with eBPFTrace with no visible performance overhead, which I think is a very, very cool. Okay. Now let's take a look about eBPF front ends, right? What exists out there and how they can be used. Again, let me steal the picture from Brandon Gregg, right, which outlines a whole bunch of different tools, right, in this case, by the scope and comparability, right, on the bottom, and how the ease of use it is, right? So if you look in this case, why we are talking about eBPFTrace here, because it's kind of in this upper column, right? It can allow us to do a lot, right? And at the same time, it's pretty user-friendly. At the same time, kind of using this bar, it's actually pretty good in terms of stage of development, right? It's a pretty stable product at this point. Now, another very cool set of tools is right here below is BCC, right? Anybody have used that? So what BCC is, right? That is sort of like I would say like a previous generation framework, right, which allowed to write some code and everything like a combination of C and Python to develop a profiling tools. But what was great about BCC is there is a thing called BCC tool collection, right, which provides, I don't know, let's say maybe 50 tools which you can use for most important, like, interesting instrumentation, right? You want to look at your I/O latency distribution, there is a tool for that, right? You want to see, hey, which connections cause like retransmits, there is a tool for that, right? You want to look into your file system cache efficiency, there is a tool for that, right? But if you want something on your to write something on your own, that was relatively brutal. And let me show how exactly brutal that is, right? That is essentially comparing code for a program which is implemented in BCC and eBPFTrace, right? I think in BCC, right, there is a lot of pretty complicated stuff, right? While eBPFTrace gives us something which is pretty user readable, right, and quite simple. So as I mentioned, BCC is fantastic. Why? Because it has a very large amount of tools which is available to instrument all kind of different things, right? And this kind of again provides us very good map, right, which shows what kind of tools allow us to get inside and in different areas, right? So lots of fantastic stuff out there. Now I think what is also interesting in this case is what now when eBPFTrace became mature enough, many of those tools are being modified and also rewritten to use eBPFTrace language, because that makes them simpler, easier to maintain, right, and so on and so forth. Okay. Now, in this talk, we are going to talk about Dtrace and eBPFTrace, right? So let's compare now between those two, right? So if you think about their landscape comparisons, right? We can put our instrumentation programs probably like in those kind of two buckets, right? Or sliding scale of them. Some very simple one-liners and some more kind of complicated analysis tools, right, which can do some complicated analysis, right, and magic. If you look at Dtrace framework, you typically can use Dtrace for your like simple one-liners and more or less simple things, right? And if you need very complicated stuff, you can use Dtrace plus shell, right, or Dtrace plus whatever programming language, right, you want to do to deal with that data Dtrace generates. If you compare that to a BPF framework, eBPF framework, right, they have a eBPFTrace, which can do a lot of a Dtrace can, but you can see Dtrace kind of can do slightly more, right? But if you need more complicated stuff, you can use BCC, right, which is pretty much powered by CLang interface to BPF bytecode, so you can pretty much implement anything you want, right, in that framework, right? And you can see that this BCC framework is kind of slightly more powerful, right, than what you can do with shell and Dtrace reasonably. Now, if you look from comparability, there is no direct comparability, right? So eBPFTrace doesn't support deprogramming language. You cannot really use the same tools, just replace the backend, and that wasn't the goal, right? The goal was to have tools which are similar in spirit, but expectations are what a lot of programs will need to be ported, right? And that kind of makes sense, because if you look between different operating systems and between different, even different versions of operating system, chances are what your diagnostic program will need changing, right? Because system calls change, right, or whatever. Here is the comparison of some of the most important functions, right, and functionality. And you can see what in many cases, right, you can see what that is. It's not direct comparison, but it really has been heavily inspired by Dtrace. Another thing we can look here is compare two scripts together side by side, right? And I recognize it's hard for you to see that on the back, but you can also see what if you look at the whole concept of a script. Again, it is relatively similar. So if you have been programming for Dtrace using D, you should be able to get started with eBPFTrace right in a relatively short time, right? And I would say if you are moving some of your programs, right, from Solaris or FreeBSD, right, in Dtrace to Linux, probably figuring out what probes to connect, right, and how they're named, that would take more time, right, than actually conversion with syntax. Okay. Now let's take a look at the eBPFTrace. So what are requirements? Now, if you look at the requirements, a lot of them actually depend on what exactly probes and interfaces you're going to use in Linux kernel. Right? And you can see if you are, for example, only using key probes, right? You can run it as easy, right, as with, well, not as easy, as early as kernel 4.1, right? If you really want to use more advanced stuff, right, for example, hardware events, right, like if you want to trace, you know, cache misses, right, and some other stuff, right, then you want to have a kernel 4.9, right? So again, similar image, right? I think this has a very good example which highlights about what kind of different probes, right, you can use for different part of your Linux systems. Okay. Now let's look at how eBPFTrace works, right? If you look at from this standpoint, right? You can think about there is eBPFTrace, that's your basically program, right? And then there is a kernel what operates in the kernel level. So when you run eBPFTrace, right, then you would have obviously the program which is going to parse, right, go through C-lang parser, right, and in the end we are going to get a BPF bytecode, right, as I mentioned, for all the generations, which is going to be loaded to the kernel, and again, similar to our in general BPF summary, right, we'll see the maps, buffer, right, and so on and so forth being available to eBPFTrace for processing, right, and printing, right. So again, very similar to a BCC framework, but kind of a little bit more complicated because there is more of things going on. So now, if you want to go ahead and use eBPFTrace today, right, what can you do? Well, first, not all distributions currently have packages, right? It's kind of relatively old too. And again, as I mentioned, because that is a high-paced development, even if you have eBPFTrace in your distribution, you may want to check and have packages from iAdvisor, right, for the latest version. Now, another way to install eBPFTrace is also to use Snap, right? But I will write on latest versions. But I will also show, right, while there is a recommendation to do that in documentation, you may have some surprises, right? Because of how Snap operates, you may not have a full functionality in the tools depending on what you want to do. Okay. Now let's look at a simple BPF program, right? BPFTrace program, right? For this is our kind of relatively simple one-liner. What is going on here? We are calling eBPFTrace, we are providing -e to execute, right? And all of that is pretty much the program which is passed. The program for us, it says, hey, we want to attach for this probe, right? And then for kind of given TID, right, you want to record in current time nanosecond, right? And then you can see key read probe, right? That says now we also want to instrument when VFS read call returns, right? And these are going to essentially put that in a histogram, right, and delete what we have stored as a start. So we have a relatively simple program, right? Basically, store current time, trace it, right, and then put it in a histogram, right, when we know the total distribution time. When we run this program, that is what we're going to to find out, right? For each process, it's going to give us the distribution of a histogram, right? In this case, I am showing one for my SCaLE process. Now, question for you: why do you think you have this kind of interesting distribution, right? And there is a lot of items coming here, when there is very little there, and then another here.
Updating an index.
What's that?
That you're updating an index.
Okay. Any other ideas?
Say the big ones is if you're writing directly to the IB data files.
Yeah, these are all for read, right? So, anyone else? Yeah. Yeah. So if you look at a lot of I/O, right, it's very frequently would have what is called bimodal distribution, right? So this is VFS, read from file system. A lot of reads here are very fast, right? These are going from a file system cache, and those are physical disk, right? So they are approximately correlated in terms of how long disk I/O takes. Right, so that is a bimodal distribution is very, very common, right, when you look at all the, file system, file I/O, right, or anything else which involves caching. Okay. So, Vic, yeah.
Sorry, I have a question. Can you go back?
What's that?
So here, I didn't follow, the histogram is showing kilobytes.
Well, this is K and M suffixes, right? The histograms, it doesn't know what you're doing.
I'm saying that the program is reading time, right?
That's right.
But the histogram is showing.
Well, the histogram here is pretty much the output for histograms, right? Is kind of designed in such a way. Right, because in eBPFTrace, you just have a function to output histogram. It doesn't know wherever you are storing bytes or seconds. Right, so it looks in this case like these are 256K, like that's a size. Now that is actually a number of nanoseconds, which corresponds to, well, whatever right it is, like probably half a millisecond, right? Which typically what I/O from SSD, right, you would expect. So, yeah, that's kind of a little bit confusion, right? They probably may clean it up in the future. Oh, do you want to have your histograms for time and histograms for data size, right? But currently it's not there. Make sense? Yeah. But yeah, thank you for catching. Okay. So, other thing, you can save it also as a script file, right? No surprises here. Some little bit better formatting, right? It just does the same thing, and then you can write it pretty much as a read BT, right? Or even put the proper header in the file, right, and make it executable, right, and run BT programs then as you run Python, right, or whatever. So, and that's how you convert the. So if you look at a concept overview, right, going through the same. If you look at the very high-level syntax concepts, you have a probe, like several probes you attach to. Then you can apply the filter, right? For example, you can say, hey, I want to attach this probe, but I only want to attach it for given process, right, with speed 1 to 3. Right. And then in the brackets you would have the action, right? That gives us a program, right? In this case we have no filter, right? That is a probe we attach to, and then right, that's pretty much the action, right, which is done, right? So. Pretty much that is the core, right, what you do in the program, right? And again, you can, in the same program, you can have a multiple of those bits and pieces, right? Like in the previous program, we attached to these probes and that probes, right? And then you kind of combine that data together, right, in a simple way. And you can obviously do it more complicated way. Okay. Tools. Right. there are a number of tools which are available, right, for BPF, and some of those tools like essentially copy, right, or replace with BCC tools functionality, right, with bio-latency, right. If somebody is familiar with BCC, they also have bio-latency, right, which can show you block device latency distribution. Now, another thing is I mentioned if you guys are interested in the bytecode for BCC, right? I don't think there is a particular way why you want that, right? And typically that's kind of for developers which may want to debug it, but there is this -v flag in BCC which can give you, you know, fantastic representation, right, of that, you know, bytecode for BCC programs, right? Well, I don't know, maybe you want to kind of get some more ideas, right, about what the hell is really going on. Now, let me show some example. I wanted to use this tool and say, hey, well, some of you may know I'm a MySQL guy, right? So I wanted to see how we can use eBPFTrace to trace something in MySQL, such as there is this function which is called dispatch command, right? That's where every MySQL query is run from that function. Now, at first, I was confused. It gives me this error. Oh, there is no such file or directory, while there was obviously a file, right? And that is what I would say with a snap package, right, becomes a problem, right? Because a snap package, it operates pretty much in its own file system namespace. It will not read the same files, right, by default, right? So I installed eBPFTrace using apt, right, instead in this case, and I have another problem right now. The symbol cannot be found. Now, anybody has an idea why? What? No, well, actually, the street binaries work, right, with eBPFTrace. That is not particular problem. If you look in this case, right, which I was to look at what exactly exists in MySQL, that you can look at in M, you would see that we do not really have dispatch command. That has been, it has this kind of some weird name, right, which is called like C++ name monkey, right? So, and reality is, I have to use that real function function name in this case to connect that, right? So finally, in this case, what I can connect to that function and say, hey, you know what? I want to print a string, right, of, you know, of a second argument. Ta-da, right? It finally shows me all the queries that MySQL is running. Obviously, I could now do the same thing as I did, connect to the start of a call, end of a call, right, and measure the time it takes to run the queries, right, and all the jazz. What I may want to. Okay.
Do you install the development libraries? The debugging libraries?
Yeah.
Can you use the real name, or you still have to use that?
Well, I mean, I haven't looked into that, right, frankly. As I understood, what you still have to use this, right? The reality is, if you look at the, you know, some arbitrary C++ command, right, you can potentially have those kind of function methods, multiple functions having the same name but different signature parameters, right? So that makes it kind of impossible in C++ to identify the function by the name alone, right? That is why that monkey is needed to begin with. Make sense?
Yes.
So, okay. So with that, I would, as I mentioned, I would encourage you to check out what I would call eBPF Bible. right, on Brandon and Greg's website. He has a lot of material out there, which goes much further than I can do in this talk. And also, I'm going to distribute the slides. Like when I was preparing for this presentation, I put together some of the helpful links, which I found helpful. So maybe it will be helpful for you as well. Yes.
So, one thing that I've not ever really understood well about eBPF,
Uh-huh.
how are the map files, the map areas, whatever you want to call them, the output of the BPF byte code, are they correlated are they per processor, or are they system-wide, and how are they correlated in time?
Well, so if you look at, again, I would say I am not eBPF expert in this case in terms of implementation, right? Semantically, you can create the maps, and these are really designed to share the data, right, from all the tracing, depending on what processor they are on, right, or what a process is. So, for example, I mentioned this tool, the bio latency, right, for example, which would provide you the histogram of a response time distribution for all the IO requests, independent on what process triggers them, right? And obviously, they can be run on all the CPUs. Now, if you look at the example I showed, I also can create this, let's say, histogram per process, right? So if I want to do that, right, or measure, let's say, performance per device or something, I can do that as well. I don't have to just have one global histogram, right? So, yeah, and there is kind of a bunch of different data structures which are available. Again, but concept is what you can get information from all your system, right? You can slice it, dice it by, whatever data you need. Okay. Okay, and then finally, I want to also highlight, if you folks are interested in open source databases, we Percona are running Percona Live conference later in the spring in Austin, Texas, coronavirus permitting. I think as if any conference those days. And with that, I am happy to take your questions if you have any. Yes.
So you mentioned on one of the slides that if the next trace points have overhead runs payload. So actually that's not true. We do have jump payload patching. So when trace points are disabled, there's no overhead.
Yeah, well, that's what I'm saying. If a trace point are disabled, then there is no overhead.
Yeah, but you said that if...
No. What I'm saying is if you have a static tracing, right? Because if you write a program without eBPFTrace and you want something to be able to enable and disable some trace in runtime, right? We often have to put in the code if logging enabled, then log something, right? For the dynamic tracing in eBPF or Dtrace, then you do not need that, right? Because you do jump table patching. That is what I meant, right? If I wasn't clear, then thank you for clarification. Okay, where else did I lie? I mean, with your Red Hat shot, you probably found a whole bunch of other things I wasn't correct. It was okay. Okay. Thank you. Okay, any other questions, corrections? Yeah, okay.
Question about memory. So, if I want, for example, to debug my memory utilization, I can find out where the memory leak is, and I know it inside my SCaLE. The problem is that how do I get into the actual function that I
the function which allocates memory. Well, look, I do not know exactly. From what I have seen in some examples, there is an access to the stack trace, right? For example, in the recent eBPF, right? So you can actually look at the allocations by the function, right, or even the chain, right? In this case. So for memory allocation debugging, I haven't seen it used for that particular purpose, right? I think in this case for memory leak checking, right, there are probably some some better tools out there, right? Because I mean, it kind of becomes quite complicated, right? In this case, what are like in terms of what is data, right, which is allocated and may be needed, and what is definitely was lost, right? Okay.
Can I use eBPF for remote monitoring services?
For what?
For a remote monitoring type thing?
Yes. Yeah, I mean, you're a good point, right? In this case, what we are actually command line tools, right? But you can also use, for example, eBPF exporter, right, which allows you to basically have those eBPF programs, right, and get the output in the Prometheus exposition format, right, then you can load in your monitoring system. And I have seen some other tools, like I think like SysDig, right, has also the monitor interface for that, right? And I think there's many monitoring tools adding now support for eBPF as well, right? Anybody knows, right? Some other monitoring tools which support eBPF? No? Okay. Yeah, you had a question.
Yeah.
Sure.
The landscape graph that you showed, some of the tools in the space and how difficult or easy they were to use, and how well developed they are.
Yeah.
Apply was up there as very easy to use as well.
Yeah.
Are you able to speak about that project at all?
Well, yeah. So if you look at Apply, right, in this case, I think Apply was, in my opinion, was a very cool tool because it provides a lot of eBPFTrace-like functionality, right, in this case, but it was relatively easy to use, right? I think the development momentum, if you look at this case right now, is probably much more of a eBPFTrace side than Apply side, right? I hope you're not Apply developer and I'm not offending you. Yeah, but yes, there is that tool out there as well. And I think that's what is wonderful in open source ecosystem, right? I mean, you find there are often many tools to do the same stuff, right? And then through years, we have like Darwinian evolution, right? And some of them die and others continue. Okay. Well, if there is no questions, then thank you for stopping by and enjoy the rest of the conference.
So y'all can just ignore me for a minute. I'm going to run a mic check because this thing keeps falling off of my ears here. The fat cat on the mat may seem to dream of nice mice that suffice for him or cream, but he, free may be false, walks in thought unbowed, proud where loud roared and fought, his kin lean and slim and deep in din, and the east feasted on beast and tender men. Okay, no feedback if I go to the edge of the stage. That's very good. Yes, it's one of the three things I do for mic tests. The other one is Hamlet's soliloquy, and then I'll do a number of other off-the-wall little things. I occasionally recite Jabberwocky, but no one in their right mind ever gets that one for this. I'm sorry? Oh, that's a good point too. Yes. Okay, mic check. For that. So the little poem, The Fat Cat, kudos for anybody who can tell me who wrote The Fat Cat. I'll give you a hint. It's a very famous author, a fantasy author. And you probably will realize that this person writes a lot of poetry in their books when I tell you. So, yes, J.R.R. Tolkien wrote The Fat Cat. And it was one of the first poems I memorized just because it's so cool. I'll give people a few more minutes to sneak in. It's 1 minute to go. And since I'm the last thing on the agenda here, I will do my best to get you out of here early. And that's exactly what I'm saying. They're going to tell me, as usual, I have 25 minutes to go through a 1-hour presentation. No problem. Got it done.
You can go all the way. It's going to be in the back and give you 5 minutes to go in.
Okay. I promise to finish early. because I also am ready to quit for the day. Okay, so let's go ahead. Okay, feedback. Let's go ahead and get started. I'm Dave McAllister, as the thing says down at the bottom. A little bit about me. I work for a company called Splunk. I've been there a grand total of 3 months. I've worked in a number of different disciplines, a number of different vendors. I've helped build some of the largest IoT environments in the world with middleware messaging. I am owned by 3 cats. I understand how to take rejection, for instance. I spent 10 years as a soccer ref. I know how to be argued with, trust me, on this. I'm married, therefore I don't read minds. If you have questions, you need to let me know and ask them. So that's a really quick summary of me. Splunk likes to talk about how everybody has 1 million data points, and we're supposed to have fancy slides about this. I figure those 3 things say everything you actually need to know about me. So what's happened a lot is that the world has changed, and over this time frame we've gone from sort of the monolithic database, middleware, front-end environment to this cloud-native environment. And part of that cloud-native environment has caused a couple of different things to happen. We've seen microservices come into play here. We've seen lift and shifts. We've seen refactorings where people are writing different things. With that has come a brand new level of complexity, and at the same point in time, we've got an instant gratification society where 5 seconds is a lost sale in e-commerce. So those 2 things are driving sort of the aspects of the things that we're going to talk about when we look at monitoring for this Kubernetes world, this microservices world. But we're really going to start off with a discussion around observability. So observability has been around for quite a while. It started with machine theory, in fact. And honestly, what's happened when I look at observability and look at it from a monitoring viewpoint is that people, but they don't observe. They've got lots of things, pieces of data, and all they're really looking at maybe are sort of the pretty pictures of what that means. But underneath that can be a lot of other things. The other way I tend to describe this, if you're getting into the observability piece, you want to check the depth of the water before you dive in head first, in all cases for this. So observability is a signal-to-noise problem. But it's actually not a signal-to-noise problem. It's a signal-with-noise problem. We need all of that data that's coming into here. And we can look at ways of taking that data down. Back to building hardware systems here, we had to worry about the signal-to-noise ratio quite often. And there were two basic ways of handling that. One, you filter it on the front end. You do a pan-pass filter, and you get the relevant data that you want inside of here, but you ignore all of your outliers. Outliers matter in observability and systems far more than the common middle ground does. The other one is you bring everything in, and then you sort it out into the things that make sense for you, and you separate out the outlier capabilities from the everything's fine type of capabilities. These two things deal with that. And red, which is what we're going to cover here, is the first pass method of looking at what filtering can do for you inside of these microservices environments. So after this slide, you can all leave. We'll be done for the day for this. But basically, observability is the quality of the system that tells us what's going on inside the system by looking at what's we can see from the outside world for that. This means a couple of things. You have to build the system to be observable. Doesn't mean you have to write code to be observable. It means your system has to have the ability to share that information. And then for engineering purposes, it really is doing that. Designing the variables so that you can see what's going on inside of your system. If you're driving a car, for instance, and the check engine light goes on, that's a piece of observable data, but it doesn't tell you much. And that's sort of the metrics viewpoint of the world here. You need to be able to look inside, see more details to understand that your oil pump just failed, your engine is overheating, and you're about to seize up. So those are where you start bringing in additional sets of information. So observability is not one-dimensional. And this is kind of where I first got started, was that people would look at this and say, oh, look at all the pretty little numbers inside of here, and we're perfectly happy because all the pretty little numbers tell us things are going okay. That's basically what monitoring is designed to do, is tell you things are going okay, and tell you when something is not going okay here. But when we start looking at this from an observability viewpoint, we actually need more data, the first set of dimensionality that comes into play here. We need the logs. We need to look at the metrics. We need to look at the traces. We need to look at events. We need to look at every piece of information we can get that makes sense for us so that we can actually determine what's going on inside of that system. All of these include metrics and time, because that's the simplified approach for what we look at. I think it's Uber. Their tracing model is 50 billion traces for every 10 minutes, and no one is going to watch every single trace. So we need to be able to aggregate up and disaggregate as we need to do it. It also needs to be crossing all the boundaries. It's not just an application issue, it's also an infrastructure issue. That's our second set of dimensions that come into play here. The first is that we have lots of data signals. The second is that we have lots of sources of those data signals. And anything that slows you down is bad. If it takes you 30 minutes to realize a problem has occurred, it's not useful. So those are the things that really break into this dimensionality picture for observability. So observability isn't just monitoring, and we'll get back to that in a minute here. It is an attribute of the system. You make the system observable, and monitoring is a verb. It's what you're doing to the system inside of here. You'll also hear about 3 pillars. We'll cover them more, but those pillars are actually made up of lots of different signals inside of here. Just in the log file information alone, you can have system logs, and you can have infrastructure logs. If you're in a Kubernetes environment, you've got the Kubernetes orchestrator logs, you've got the worker node logs, you've got the pods, you've got the containers, and you have the application. That's just a log thing. Ran into a problem about 4 months ago where one single customer in a very large environment was slowing down on their ingest. Everything else in the system was running fine. The system is 1,500 cores, and the user was using probably 16 to 20 of those cores, and was slowing down, and we couldn't figure out why. We actually had to go all the way down into the thread logs of the CPU cores themselves to figure out what was going on inside of the system. And interestingly enough, what happened was we turned out when we started unraveling this thing, which took people a lot smarter than me, 2 full days to do this, to figure it out, what it turned out was somebody had misconfigured the queue depths and failed to set the queue depths to fail over and build more queues. And their queue alone was filling up and everybody else's was fine. So that's an indication of all the signals that come into play here. You're also going to need signals you've never thought of before. Observability is about finding the unknowns inside of our system. Monitoring is about finding the knowns of the system for here. So all of a sudden you're going to find things that you never thought of before. I would have flat out told you 5 months ago you would never need to look at a thread log unless you were writing compilers. Guess what? I was wrong. So we do have 3 pillars that come into play here. And you'll see them as metrics. Do I have a problem? This is where you detect what's going on inside of here. Traces, where is the problem? This is the troubleshooting aspect of this. And then finally, logs, what is the problem? That pinpoints those things. These are our 3 pillars. Those pillars can be made up of lots of different signals, but these are the 3 aspects that make up an observability space. Everything is an event. Events, traces, metrics, whatever. Everything is an event. If it isn't recorded and measured, it didn't happen. Keep that in mind. Which means that if somebody is sampling, if you're pulling a sample data out and you pull 1 out of 10, you're missing 90%. It means you're missing all your outliers. This is why sampling does not work in this environment here. Metrics, efficient beyond belief, 100 million metrics per minute, no problem inside of here. Logs, full fidelity, but it's dependent on who decided what to put in the log file. My previous company, we had an engineer who thought it was really cute to put in his log entries in Russian. Okay, none of our DevOps speak Russian. That was problem number 1. We did get him to change it. So he did. He changed it, put in English that said, "Here I am," in every single one of his log entries. He no longer works for that company, by the way here. Traces are really cool, but they take additional work inside of here. Logs are bulky at full fidelity. Traces make logs look efficient and slim. For every single set of a transaction, a log file may write off 8 entries inside of a single e-commerce transaction. The traces for that will be about 150 to 200 traces, pieces of information. And so you've now got this full fidelity aspect inside of here. And I love this cartoon because history is the fiction that we invent to persuade ourselves that events are knowable and that life has order and direction. Well, it's true. But the problem is that we are creating history every time our application goes through a request. So it's not past history, it's present history, and that's what observability shows us. So expect that you're familiar with microservices architectures, but this is an example of a microservice architecture based off of the Amazon ordering page alone. It's a little out of date. I haven't updated it here, but you can count real quickly. There are 3, 5, 8, 10, 11 separate microservices just for the order page alone. By the way, this isn't actually fulfilling the order. This is just that page has that many microservices attached to it. Expand that times the number of people that are making use of this. Add into it the back ends, credit cards, currency exchange, fraud checks. All those different things become more and more. It is easy that something like this page, once it's completed a transaction, is going to have something around the neighborhood of 200 to 250 services it touches. Some of those are standard third-party packages. Some of those are written. A lot of those, this is Amazon, a lot of those are open source that we never get to actually see what they did to change it, but it's there as well. But nonetheless, there's a lot of microservices. These microservices interact in unique ways. And because of that, we need to be able to trace, this is where tracing comes in, the pathway that your request took as it moved through the system. Kubernetes, which is the other side. While we had microservices before we had Kubernetes, Kubernetes makes life a whole hell of a lot easier in dealing with microservices, particularly container-based, cloud-based. And basically what it's going to do is keep track of everything that I've asked it to build, put it into the environment to which it can be built, and make sure that things are running smoothly. However, back to this complexity issue, Kubernetes adds layers of infrastructure that we didn't have to worry about before. You've got the orchestrator itself, you've got the worker nodes, you've got pods, you've got containers, and you've got apps. We used to just worry about apps and servers. And then we worried about containers, apps, and servers, servers necessarily being virtual inside of here. And now we have multiple pieces. And we have to worry about it because Kubernetes is built to be failover capable itself. So we've got to worry about multiple master-slave relationships that happen inside of that at the same point in time. There's a control plane that figures out where you want and how you want to deal with this, and it keeps things running smoothly. What that means is you need to observe all of those pieces as well, not just your application, but the control functionalities that deal with that and all the infrastructure pieces. This is important because it's ephemeral. Things are not always there. And honestly, unless you go figure out where it is, you have no idea where Kubernetes puts something. You can tell it what kind of things to put, what systems you're looking for, but you don't get to say, put it on server A. Only if server A is the only thing that meets the qualifications. And so we're now having to observe the state of systems that we don't know where they are until we observe them. So it's amazing how confusing this is, and I figure that it shouldn't be called, I think it should be called Schrodinger's observability, because the system is either alive or dead, but we don't get to know until we look at it for that. So observability, I think this is my last slide to talk about observability, is actually a loop problem. In machine theory, I used to build process control software for plants that automate and run themselves. There are two aspects of observability. One aspect is what is it doing? What can I see? And then the second aspect is called controllability. The way that we get data in and out is called telemetry. And then in machine theory, those are the three pieces that make up this cycle here. Observability is the ability to see these things, and it's made up of that log, traces, metrics, and whatever. We need to close this loop. Observability needs to have a closed loop here. And that loop closure can be automated so that the system itself knows how to fix things. You release a new microservice. The microservice causes errors to show up someplace else. The system can roll back to a no less known stable state automatically for you. Or it can say, oh, great, look, there's a problem. Let me send an alert out, send out a Slack message, have somebody's phone go off, and have them look at it. And that's an open loop. But both of them complete the loop. This is something that's missing when we tend to talk about this space, is everybody looks at this as a see something and say something problem, where it should be a see something and do something problem for that. So why red? Why Kubernetes inside of here? Complexity matters. We have a lot of complexity that actually makes our life easier, but not simpler inside of here. There are lots of moving parts. There are lots of interrelations inside of here, and there are lots of things that aren't there when we go to find out what happened. Again, in a Kubernetes space, if a pod dies, every piece of information it has had about what was going on in that pod dies with it. Unless you take the action to save it off, you will not know what happened to your pod. And so you need to be able to make sure that that's going on inside of that. We need to have simplicity to help reduce some of this clutter. Again, this is not filter on the front end, filter on the back end for that. And then we need to be able to retain that complexity so that we can drill into it. You can think of this in terms of aggregation. I'm going to aggregate things together to something that makes sense, but when I need to, I'll pick it apart so that I can find out what was inside of it that made up that set of information. Excuse me, real quick. There's the other headache. I think I was never had any allergies until I moved to California and the trees start blooming, which means that I sneeze between January to June and then October to December, very honestly here. So what is RED? RED is actually a subset of Google's SRE environment called the Golden Signals. And it's originally built by a guy named Tom Wilkie, who at that point in time worked for Weaveworks. And it's made up of 3 topics: rate, errors, and duration. And you can actually break this down and go, rate is metric, errors are logs, and duration is tracing. But that's oversimplifying in some ways here. He originally designed this for request-driven microservices. But it actually turns out it works for anything that is request-driven. It doesn't have to be microservices-based, which means that if you have a standard environment that has a request that you can track, and it goes through and comes back, you can run a RED environment against that. And as you can tell, what happens is I have over here my microservices. I'm showing the request rate. So this one is running almost about 10. I'm showing an error rate, which is currently at 51% for that one. I think there might be a problem here. And my duration is broken into two aspects. I'm showing the percentage at 50, and I'm showing the percentage at 90 inside of that. That information alone gives me an amazing amount of information, but not enough. Very honestly, I can say there is something wrong going on here. 51% error rate's a little bit off the extreme, but it's not time-based. And so all of a sudden I've got those 2 pieces inside of here. And as I look down, I can say, oh, well, maybe there's something going on here. There's a 29% showing up in catalog, and there's a 55 showing up in payment. So now I can start drilling in to figure out what's going on inside of those things. But RED is the ability to take all that massive amount of data from all those different pieces and run it into something that you can very quickly determine whether you have an error and where the error exists. Think of it this way. RED is monitoring at Chuck Norris level. Chuck Norris took action. He didn't just see things, he actually did something with it for this. By the way, that joke does not work in Spain, but it does work in Japan, interesting enough here. So again, metrics, logs, traces make up this rate environment here, and it gives you both the recognition of issue and the recognition of the root causes that take part inside of this larger environment. So rate, very simple. How many things are flowing through the system? You can think of this in terms of bandwidth, overall bandwidth. You can think of this in terms of individual calls, be they HTTP calls, SOAP calls, REST calls, API calls, whatever one. You can break it down into any way you want to look at how many things are going through your system. Very honestly, to quote John Massey, very famous computer scientist from the 90s, bandwidth costs money. And so knowing this gives us the ability to look at what our systems overall are doing. You can actually use this in anything that can fail on bandwidth. So if your bandwidth shoots up high, you may have a problem. Maybe you need more systems. If your bandwidth suddenly goes to 0 and it's Black Friday and you're Amazon, you have a different problem. So your bandwidth your rates can measure both directions going on here. Quick example, 10.3 request. I can see what my request rate works at in this particular model. It's a 10-second model. I can see where the endpoints are, what endpoints are making the most requests that are going on inside of here, and I can break it down by endpoints that go into each of those pieces. I can actually, again, take a RED environment and build out more and more information. Again, I've got the underlying structure, even though I'm starting with a number that says 10.3. I can now disaggregate to get more information out of a RED environment. Errors, everybody kind of knows what errors are. Something that gives me an incorrect, incomplete, or unexpected result. That's an error inside of here. And it can be lots of places. It can be something that's wrong in code. It can be something that's wrong in infrastructure. It can be peak load. It can be communication problems. One of the worst possible scenarios is when you have 2 of those that hit you at the same time. That will still show up as errors. And again, you'll have to be able to disaggregate to get down to what's going on here. Errors are the thing that need immediate response. Literally, in the time I told us they made that statement, you probably need to figure out what's going on with errors and get back to a stable state somewhere inside of your environment. You can't necessarily sit around and wait for it to happen inside of that. It needs deep diving. It needs high fidelity functionality, because you're going to want to go right down into the specific spot and the specific report of what went wrong with that system inside of here. And reflecting once again, It's now. There is no tomorrow when you're dealing with an error. One of the lines I do like to add here, because this gets brought up, is that, oh, we catch all these things in testing. Sorry, testing for production is not running in production. Prime Day of 2017, Amazon spent 5 hours not able to process orders. They rolled out a new service that was supposed to be able to deal with an elastic expansion of the order system on Prime Day, which passed testing just fine and failed in production because they didn't expect the volume of traffic to hit them in the first point in time. By the way, that's $386,000 per minute of lost revenue. 336, sorry. So errors are usually reported in error rates, again, so I can look and see I've got a percentage of error rate that's happening inside of here. The error rate that's happening reflects back to your rate, how many things are coming in. So if I've got 10 things coming in, 4.5 of them are failing. Since it's averaged out over 10 seconds, it varies across here. But again, I can look at its rate over a very tight time frame. I can look at it from endpoint, and I can drill into any particular point by simply drilling down into that error logging type of information that's going on. And so one of the things that's useful is where you can step into it, click on a dot, and see specifically what its pieces of information are. And duration is all about time. And this is the realm of distributed tracing. These days, with CNCF, we have open tracing. We have the outside project from Google called Open Census, and we have the new Sandbox project, which combines open tracing and open census together to become open telemetry. Open telemetry provides all those aspects, APIs, plus the metric-defined environments, plus the ability to hand it off to tools to actually show you what's going on inside of here. Its job is to bring things into order. That's really what its job is, and to tell you how long things took. Now, that headache used to be that distributed tracing required you to re-instrument your code base. But now we have a lot of techniques that allow us to look at what's going on inside it, because one of the major portions is between the service endpoints. And so we need to be able to measure the points of communication, which is in the network phase. You'll hear a lot about service meshes, Istio, Envoy Proxy, Linkerd, all those different pieces provide that information. And every one of them provides you a distributed tracing environment pretty much out of the box. You can also use instrumented libraries, not touch your code, but instrument the library that allows you to see what's going on there as well. What it does is tells you what happened in the event, how long it took, somewhat to a point of why it took that long, and then what microservice or service was responsible for the delay. In a microservices environment, quite often when we see errors, they have nothing to do with the service that reported the error. Quite often they are somewhere else in the environment. And tracing will help you figure out where the original backtraced error came from, so that you can start narrowing in on the root cause as fast as possible. Duration examples, again, you'll see them usually as an aggregate number. You'll bring them up. Again, this one's a 10-second example for this. The aggregate number then shows you out to the distributions, which then can show you out to the endpoints. The other thing that tracing will do for you is show you what's called a service map. It will show you the process, the mapping of where your actual request went through your system. So imagine, for instance, you are, again, a big e-commerce shop. You've got lots of front ends coming in here, each of those generating a request. That request goes to some collection, elastic or not, of services. And you need to be able to trace through what happened for that specific request, because, again, the infrastructure matters to the application as well. So why red? Well, red's easy to remember, very honestly. It also, we found, when I was doing consulting, we found that it's easy for teams to agree to start with red. It's a common language. It's a very simple method to be able to say this very complex world can look like this, and then we can expand to figure out what else we need. In a microservices environment, again, Teams don't work on all the microservices. Individual teams will work on multiple pieces of those microservices environments. And Red gives them that common vocabulary to say, hey, I saw a activity that the rates went down here, and I saw an error here, and my duration went screaming up around here. And everybody knows what it means. And so it provides a common language here, a consistency that crosses multiple teams and multiple geographies. The other thing is that since Red is a fairly well-defined environment, you can automate around it. When a red alert occurs, you actually know what the red alert means. And so then you can start doing automation. Red alert happens. Look and see what happened inside the system. Look and see if there's been a new deployment of a service here. Roll back the service. All those things are automatable. All those things are can be managed, even if they're not automated, directly through runbooks. And so we can get the respond aspect of your system, returning stability out faster with a red place environment here. And interestingly enough, it serves as a proxy for user happiness. Users really are interested in, did my request make it through, and did it happen in time? E-commerce, 5 seconds is a lost sale. 10 seconds, he was somebody who will go complain on social media or to their friends about how slow you are. So a Google study from 2017 pretty much defines it that way for here. So if you look at this and you start looking and seeing what your rates are going through correctly, your timing is going through correctly, you probably have happy customers, at least with your applications. Pricing is somebody else's problem. So here's the downside. This looks really cool. Rate, error, duration. I've only got to worry about 3 things. But every one of those pieces can impact something else inside of this picture. So I have an error. The error is causing me to have, I'll pick on the infrastructure. I have a flaky network card. The network card is causing my rate to drop, my error rate to go up, and my duration of the things that are completing are fine. So even though I can figure out what's going on inside of here, each piece, I can have a high rate that is not showing me an error. I have a high rate, it's causing me a duration problem because my bandwidth is saturated. So all of a sudden, I've suddenly got a slow consumer model that's happening inside of here. So each piece can have a correlating effect that may or may not show up inside of the one that's causing the problem. And this is where Red gets a little bit tricky, and you need to be able to watch and understand what the balances are. This is also why you need to always be able to show all 3 at the same time, because that will give you an indicator that something else is triggering this piece over here. So it's also not infrastructure, and it's not application, it's both. And if somebody is looking at this and saying, we can tell you everything about your application, it's not going to help you. And if they say, we can tell you everything about your infrastructure, it's also not going to help you. In a Red environment, in a microservices environment, these 2 pieces work in lockstep, and you have to be able to look at both of them here. Tools should be able to help you out here, but if all they're doing is showing you pretty numbers, don't go there. You'll spend more time setting up pretty numbers to be able to not have the data that's inside of here. Doesn't mean you can't use things that produce pretty numbers. So for instance, Prometheus is an amazingly cool metrics tool that happens to have the ability to produce Red inside of here. But what you're going to want somewhere is the ability to drill into what it's telling you is causing those numbers to change. And I fully love Prometheus. I was one of the early guys who jumped on this and dragged it into companies kicking and screaming, and only one of them actually kicked me out because of that. But nonetheless, that's the model. So Red can uncover, overall, the problems that are riding inside of your microservices, under Kubernetes or under any other orchestration model that you may be interested in. But you need to be able to make sure that you have the ability to drill into it. A little bit of sort of the zen of this. There are really only 2 views that matter to this model. One of them is that external customer's view that I talked about, and they care about request, its latency, and whether it was successful. And again, if you think about this, that's rate, error, and duration inside of that. The operator's view is that pluralized. It's the requests that go in here, the rates, and the concurrency that's happening, as well as whether the errors are, and the operator cares about the infrastructure and what the infrastructure is doing. So that's sort of the Zen model. When you look at these two things, you get to be able to look at the user viewpoint as well as look at the system operator viewpoint for red. Some philosophy. I ran a nonprofit for Stanford University called Philosophy Talk. The hardest job in the world is to get two fully tenured professors of philosophy to agree on anything. Even if they are in complete agreement, they won't agree. I mean, it's painful. But nonetheless, so I always throw some philosophy in here. So instrumentation is not the answer. It may help you find the answer. Just because you instrument doesn't mean that you're going to magically find out what's going on inside of here. Metrics are powerful. Don't live without metrics, but they're not sufficient. You've got to be able to drill into this. Cardinality matters in this space. The ability to slice and dice and find new pieces of information. Back to remember, we're looking at unknown unknowns inside of here. So we don't know what we're looking for until we have to go find it. So cardinality matters in this space here. You also want to look at the work that's going on, not the service, but you're going to watch the service anyway. But when you're looking at the service, think about how it works in relation to the work that's going on inside of that. And your goal is not observability. Your goal is reducing the mean time to detection, the mean time to respond, and the mean time to resolve any underlying problem. That is my final philosophy statement here is, the observability is not the goal. Observability is a method of reaching that goal. So observability is more than monitoring, but it starts with monitoring. Everything starts with monitoring. If you can't see it, it didn't exist for that. Red wins on microservices applications because it gives us a common environment. It lets us cross those boundaries. It lets us look at all the pieces of information we need to determine that everything is working right, and when something isn't working right, where it's not working right and why it's not working right as fast as possible here. Red particularly simplifies Kubernetes while letting you still have the insights that are necessary to make this job happen here. And keep in mind that those red sections interact in ways that may take a little bit of experimentation to determine exactly what is causing that functionality to happen here. And finally, find the right tool. It doesn't mean there's a specific tool. I wouldn't recommend one. If you want to start with, a standard model of 3 environments here, you can go grab, a Prometheus environment, you can grab a Zipkin environment, and you can grab whatever your favorite log tool is, grep, whatever, and it will give you the same functionality. But the tool will help you get to the results faster if it all works together in one place. And with that, I'd like to thank you for your time, and I've got you 35 minutes. Wow. So, and at this point, we can maybe make a happy hour. So, for this, questions before I get off stage? Yes.
A, I love that you mentioned linkerd. That's awesome. 2, tracing. Do you distinguish between tracing and distributed tracing?
So we've been tracing for years. Very honestly, for that. So yes. So there is the concept of tracing that, for instance, has lived inside of machine code for years for this. Distributed tracing is the ability to extend that trace across multiple systems and multiple boundaries. That's really what it comes down to.
That's how I think it. I just want to make sure.
Yep.
And then to find the right tool, we often talk about having a toolkit.
Yes.
So would you say that you talk about finding the right tool just for a specific piece of observability?
So you're correct in that there are a minimum of 3 tools. And yeah, my company has a set of tools inside of here, but it is not my limiting factor when I go to a customer site environment for this. For instance, my company doesn't offer Prometheus, but I make sure that if you are interested in Prometheus or you have a specific use case that Prometheus meets really, really well, I want to be able to pull it in. The integration of the tools matters. Okay, it's like, it's sort of, using car analogies again here, it's sort of the difference between having a socket wrench and having a set of box-in wrenches. A socket wrench, I'm going to be able to pop in and out and find the right piece I want. It's a smaller, more complex concrete piece here. I have a full set of box wrenches because if something strips, the box wrench is magic for making that happen. But I've got to go dig through and find the right one. So yes, it is a tool chain is actually the way I prefer it versus a tool set.
Thank you.
Sure. Questions? If not, I'm going to give you 20 minutes back of your life. Thanks for coming out and listening to me. And enjoy the rest of the show.